session, we are going to discuss little bit more about the concept called memory management. So before starting with the today's session, if my voice is clear as well as able to see the screen properly, please type 1 in the chat box. If my voice is clear as well as able to see the screen properly, please type 1 in the chat box. Okay, thank you very much. Thank you very much. If you see what is the discussion happened in the last session, in the last session, we are trying to understand something about semaphores. We are trying to understand why we required synchronization between the threads. Okay, why we required the synchronization between the threads, and what is the difference between the semaphore and a thread, semaphore and mutex, that we are trying to understand. After that, we started thinking about the concept of memory management. Ultimately, the opcodes are going to be fetched from the RAM and it is going to be executed. Will you agree? Ultimately, the opcodes are going to be fetched and going to be executed. Now my question is, who will do the fetching, decoding and executing job? My question is, who is responsible for doing the fetching the instruction, decoding the instruction and executing the instruction? Can I say the processor or a controller? Listen, now in an operating system environment where the instructions are going to be present, in operating system environment where that instructions are going to be present, the instructions are going to be present in the RAM. So yesterday we are trying to understand the concept called address binding. The opcodes need to go and sit into the RAM location. Again, the opcodes need to sit into the RAM location, and it need to, CPU need to, processor need to fetch that instructions. So the binding between the opcode and the RAM location can be done in a 3 different phases, 3 different stages. Binding between opcode and the RAM location can be done in a 3 different phases. One is a compile time binding, and another one is a load time binding, and another one is a runtime binding. If at the time of compilation only, when the opcodes are generated by the compiler, at the time of compilation only, the binding is happened, means this opcode need to go and sit into this location, this opcode need to go and sit into this location, this opcode need to go and sit into this location. If compile time only it is decided, such type of code is called as raw code. So your microcontroller is one of the best example for the raw code. At the compile time only, the opcode hex file is generated in such a way that, so this code need to go and sit into which location is decided at compile time. One more thing is there, that is called as relocatable code. So that location binding is done at, can you tell me, in a relocatable code, the location binding is done at, in relocatable code, the location binding is done at load time. And executable code, the location binding is done at executable code, the location binding is done at runtime. So to achieve this runtime binding, we need a separate hardware unit. To achieve this runtime binding, we need a separate hardware unit that is called MMU. After this, we started working on memory management. older versions of memory manager, what is the method they followed for managing the RAM space, that we are trying to understand. Again, in the older versions of operating system, the memory manager, what is the method, what is the policy, what is the procedure they followed for managing the RAM, that we are trying to understand. What is that policy is called? What is that policy is called? Partitioning method. That policy is called as a partitioning method. There are two uh, categories are there about this partitioning. One is fixed partitioning method and another one is the dynamic partitioning method. In a fixed partitioning method, again two subcategories are there. Fixed equal size partitioning, fixed unequal size partitioning. Can you tell me in which policy more internal fragmentation is there? Fixed equal size or fixed unequal size? In which policy, in which method, in which procedure the more internal fragmentation happens, more memory gets wasted? That is, can I say, fixed equal size partitioning. To overcome that internal, what is the meaning of internal fragmentation? Yesterday I told you, what is the meaning of internal fragmentation. In a fixed partitioning method, a process may get more than the required memory. In a fixed partitioning method, a process may get more than the required memory. A process may get more than the required memory. That is called as internal fragmentation. So, to overcome this internal fragmentation, they introduced one new policy. What is that? To overcome this internal fragmentation, they introduced a new policy that is called dynamic partitioning. Will you agree? That is called dynamic partitioning. In a dynamic partitioning method, which problem is solved and which problem came? In a dynamic partitioning method, which problem solved and which problem came? Can I say, in a dynamic partitioning, internal fragmentation problem gets solved, but new problem is erased. What is that? But new problem is erased. What is that? External fragmentation. Yesterday we are trying to understand with one example. I'll try to represent that one more time. Suppose this is the RAM. Suppose here P1 process is there. P1 process which required suppose 8 MB. Just a minute. There P1 process which required 8 MB. Just give me 1 minute of time. This my pen marker is not working. Which required 8 MB. P2 process is there. Just a minute. P2 process is there. There is a problem with my this one. Please wait. Just give me 1 minute of time. I'll change this pen tab. Just give me 1 minute of time. Okay, now let's see. Suppose this is my RAM. I'm talking about the dynamic partitioning. Suppose P1 process required 8 MB it required 8 MB, it is allocated 8 MB. Suppose P2 process required 7 MB, 7 MB is allocated. Suppose P3 process required 5 MB, 5 MB is allocated. Suppose P4 process required 6 MB, 6 MB is allocated. And suppose this 10 MB is free. Suppose this 10 MB is free. And suppose P1 process execution is completed. So can I say P1 process execution is completed. Suppose P1 process execution is completed. Now can you tell me how much of MB of the memory is totally free? Suppose P1 process execution is completed. Can you tell me how much of total MB of memory is free? Can I say 10 plus 8? 10 plus 8. Can I say total 18 MB of the memory is free? This is free because it is P1 process is completed. Total 18 MB is free. But a new process came P5 which required 12 MB. Can I say that process is not going to get the RAM space for execution? A new process came which required 12 MB. Even though 18 MB is there, but 12 MB is not contiguously available, can I say that process will not get the RAM space for execution? So what is the meaning of external fragmentation? For a process in a dynamic partitioning method, for a process, memory is available but not in contiguously. Again, what is the meaning of external fragmentation? For a process in a dynamic partitioning method, for a process, memory is available but not in contiguously. Memory is available but not in contiguously. So that is a external fragmentation. Can you tell me what is the solution for this? Can you tell me what is the solution for this? Yesterday we discussed it. Can you tell me what is the solution for this? Can I say that is a defragmentation? Defragmentation means, what is the meaning of defragmentation? Can I say all the running processes should be shifted at one side? All the running processes should be shifted at one side. Free space is made at another side. Again, all the running processes is shifted at one side and free space is made at another side. So what is the problem with this defragmentation? Can you tell me what is the problem with this defragmentation? What is the problem with this defragmentation? The problem with this defragmentation is throughput suffers. The problem with this defragmentation is throughput suffers. Throughput means, can I say number of processes are completed within a unit of time. Number of processes are completed within a unit of time. Number of processes are completed within a unit of time. Now throughput suffers. So I hope you are understanding. For one problem, one solution came. What is that problem? Internal fragmentation. Solution is what? Dynamic partitioning. Again, for internal fragmentation, the solution is dynamic partitioning. But in a dynamic partitioning, there is no internal fragmentation, but external fragmentation is there. One more problem came. In a dynamic partitioning, internal fragmentation problem gets solved, but external fragmentation problem came. Internal fragmentation problem is solved, but external fragmentation problem came. To overcome that, they introduced one more policy. What is it? To overcome that, they introduced one more policy. What is that? Defragmentation. For defragmentation, that external fragmentation concept is problem solved, but new problem is raised. Processes execution becomes delayed. In a defragmentation, external fragmentation problem gets solved, but a new problem is raised. What is it? New problem is raised. What is it? Throughput suffers because all the processes should be stopped for a while at the time of defragmentation. All the processes should be stopped for a while at the time of defragmentation. Will you agree? Throughput suffers there. So to overcome all these problems, a new policy is introduced that we need to discuss today. To overcome all these problems, to utilize the RAM space more effectively, to overcome these problems, to utilize the RAM space more effectively, entire policy is changed, entire procedure is changed, entire method is changed. We need to discuss that method now. Now, one thing I need to ask you, if suppose my process is having, if suppose my process is having 20,000 instructions, do you think that all these instructions are going to execute at a time? Again, suppose if my process is having, my program is having 20,000 instructions, is all these instructions are going to execute at a time or not? Answer is no. Answer is no. Second thing I need to ask you, hardware related. Can you tell me in your laptop how much of hard disk space is there? Can anybody tell me, those who are having their personal laptops, how much of hard disk space is there? How much hard disk space? Can I say 500 GB, maybe 1 TB? Yes, sir. But what about the RAM? What about the RAM? What about the RAM? 8 GB. My question is, as we wish, can we increment the RAM size? Or is there any processor supporting required there? Again, as we wish, how much of memory we required? Can we connect 1 TB of RAM to your laptop? Can you connect 1 TB of RAM to your laptop? Is there any relation between the processor and this RAM space? Is there any relation between the processor and this RAM space? Will you agree? As you wish, you cannot increase the RAM size. Will you agree? As you wish, you cannot increase the RAM size physically. As you wish, you cannot increase the RAM size physically. If you accept this point, type 1 in the chat box. As you wish, you cannot increase. It is not possible to increase the RAM size. So internally, the address bus, data bus concept will be there. Internally, the address bus and data bus concept will be there. Will you agree? You cannot increase the RAM size as you wish. Physically, you cannot. So what the operating system designers, what they thought, what they got an idea is, anyway we cannot increase the physically RAM size. If you want to increase the physically the RAM size, entire hardware architecture need to be changed. Will you agree? If you want to increase the RAM size as you wish, you need to change the entire hardware architecture. Yes or no? So instead of changing the entire hardware architecture, the operating system designers, they got some idea that is called, why can't we take the help of hard disk? Why can't they take the help of hard disk? There the point came, that is called virtual memory. Yes, BE9P2, absolutely correct. Without increasing the, without physically increasing the RAM size, virtually they are trying to increase the RAM size by taking the help of, the space in the hard disk. Again, if you want to increase the RAM size physically, the entire hardware architecture need to be changed. So without increasing the hardware, without changing the hardware architecture, can't we create logically the RAM? Means answer is yes. Can't we create virtually the RAM? Means answer is yes. That is the concept called virtual memory. Are you getting the point? Where the virtual memory is present? Where the virtual memory is present? Is it present in the RAM or in the hard disk? When I say virtual memory is present in the, hard disk, but it acts as virtual memory present in the hard disk, but it acts as RAM. Now suppose this is the MMU. I need to use one term here, MMU, memory management unit. That is a separate hardware unit. Just a minute. This is the processor. This is the processor, microprocessor. And this is the memory manager. Now I'm going to discuss a new policy, new method, new procedure of utilizing the RAM space more effectively. That concept is called as virtual memory. In a virtual memory, some portion of the hard disk is taken as a virtual memory, which is divided into small portions. Those are called as, those are called as pages. So virtual memory is divided into small parts. Those are called as pages. Page 1, page 2, page 3, page 4. And physical memory is divided into small parts. Those are called as frames. Again, the physical memory is divided into small parts. Those are called as frames. Again, the logical virtual memory is divided into pages. Physical memory is divided into frames. I'll write these points here. In new policy of managing the RAM, I'll write it here. In new method of managing the RAM and increase the RAM, virtual memory concept came. In new method of managing and increasing the RAM, virtual memory concept came. Virtual memory is present in the hard disk. Virtual memory is present in hard disk, but virtual memory is present in hard disk but acts as RAM. Virtual memory is present in the hard disk, but it acts as a RAM. Virtual memory is divided into small portions called as virtual memory is divided into small portions. Those are called as pages. And physical memory is divided into small portions called as physical memory is divided into small portions called as frames. Again, virtual memory is divided into small portions called as a pages, and physical memory is divided into small portions called as a frames. And page size and frame size is same, but number of pages is more than are more than frames. Or if you read this point 2 times in this new method, because physically we cannot increase the RAM size, the operating system designers, they got an idea, why can't we increase logically the RAM size by taking the help of the operating system designers, they got an idea, why can't we increase the RAM size logically by taking the help of hard disk. So some portion of the hard disk, it acts as RAM, that is technically called as some portion of the hard disk, it acts as a RAM, technically called as virtual memory. That virtual memory is divided into small portions. Those are called as a pages. The small portions, those are called as a pages. And the physical memory is divided into small portions, that is called as a frames. Number of pages are more compared to the number of frames. All of you are getting the point? Type 2 in the chat box. Number of pages are more compared to the number of frames. Now try to understand. Just now you told that all the instructions of one process is not going to execute at a moment. Will you agree? All the instructions of one process is not going to execute at a moment. So if that is the case, now what happens is my ADAT-out is not loaded directly into the physical RAM. My ADAT-out is not loaded into physical RAM. It is divided into, my executable file is not loaded into the physical RAM. It loaded into the pages. So P1.0, P1.1, P1.2, P1.3, like this pages. All of you are getting the point? This loaded into the pages. So from the page, depends upon the request. From the page, depends upon the request, it is going to loaded into. From the page, depends on the request, it is going to loaded into. From the page, depends on the request, it is going to loaded into. Depends upon the request, it is going to loaded into the frames. Again, from the page, depends on the request, it is going to be loaded into the frames. All of you are getting the point? From the page, depends on the request, it is going to be loaded into the frame. My question is the entire process is going to be loaded, or a portion of process is going to be loaded? My question is the entire process is going to be loaded, or the portion of process is going to be loaded? Will you agree? a portion of process is going to be loaded. Will you agree? A portion of process is going to be loaded. Now, can you tell me what is the advantage of this type of scenario? Can I say RAM space is utilized more effectively? Unnecessarily, the 20,000 instructions cannot be present in the RAM. Will you agree? Unnecessarily, the 20,000 instructions cannot be present in the RAM. It is present in where? It is present in where? It is present in where? Can I say it is present in pages? So depends upon the demand, those pages are going to be loaded into the frame. Depends upon the demand, those pages are going to be loaded into the frame. Little bit detailed, we'll discuss it. Observe. Little bit detailed, let's discuss it. Observe. This page is from, just a minute. This page is from 0 to 99. So tell me, this page is 0 to 99 means what is the size? 100 bytes. This page is 100 to 199. This page is 199. 200 to 299. Like this, the pages are divided. Suppose, again this pen also problem because I don't know what happens. So each page size I considered as 100 bytes. So if each page size is 100 bytes, can I say the frame size is also 100 bytes? Each page size is 100 bytes. Will you agree the frame size is also 100 bytes? Suppose in this frame, first frame, already one process is there, P2 process. Here already P3 process is there. P3 process is there. Process, not the total process, a small portion of the process. Again, in this first frame, P2 process, one portion of the process is there. Here another portion of P3 process is there. Now suppose, I hope all of you know what is a program counter holds. I hope all of you know what is a program counter holds. Address of next instruction. Actually, this program counter is holding 150. Suppose this 150, again there is a, it's not a problem with a pen, it is a problem with my OS, I think. Suppose it is my program counter is holding 150. Suppose if my program counter is holding 150, that 150 is not the this address, RAM address. 150 is nothing but the 150 is nothing but the, what is that? Virtual memory address. 150 is nothing but the virtual memory address. So then what this MMU will do, it will convert that 150 virtual memory into virtual address into the physical address. What this MMU will do is it will convert the logical address into the physical address. It will convert the logical address into the physical address. Just a minute. So whatever this address is there, 150, whatever the address is there, this 150, this is not the physical address, this is a virtual address. So then what the MMU will do, it will try to convert that into the physical address. All of you are getting the point? What that MMU will do, it will try to convert that logical address into the physical address. This address contains logical address contains page number plus offset. Logical address, what it contains? The page number plus offset. Try to understand. So for example, first page 50th offset. The first page 50th offset. So what the MMU will do? MMU will check, is this first page is already present in any one of the frame or not, it will check. For that it will maintain the page table. Again, try to understand. What is the program counter is holding now? What is the program counter is holding now? One address called 150. That is a logical address. Now I am discussing how that logical address is converted into the physical address. The logical address or virtual address contains two things in it. One is the page number and another one is the page number and another one is the offset. So what the MMU will do is, what this MMU will do, it will convert this logical address into physical address. It will convert the logical address into physical address. You may get a doubt, sir, how it will convert? For that, MMU will maintain one table that is called page table. What the page table contains? Page number and frame number. What that page table contains? Page number and frame number. Meaning is which page is present in which frame, which page is present in which frame, that will be there in this table. Now tell me, which page we required here? Here, which page we required? Page number, which page we required? First page. Now it will check, is the first page is available any one of the frame or not, it will check. Is the first page is available in the frame or not, it will check. Who will check? Is the first page is available in the any one of the frame or not, it will check. Who will check? MMU will check this table. Memory management unit will check this table. If the first page is not available in any one of the frame, MMU will internally page fault occurs. Again, if the required page is not available in any one of the frame, what happens? Page fault error comes, interrupt comes. Again, try to understand what the MMU will do. Whatever the address you given to the MMU, that address is a logical address. It will try to convert that virtual address into the physical address. In this conversion process, whatever the logical address you supplied, it will divide it into two halves. One is the page number and another one is the offset. After converting that page number into address into page number and offset, MMU will check the page table. So in that page table, the desired page is not available in any one of the frame. What happens? Page fault occurs. I'll give the definitions clearly later. First, try to understand the theory. After that, I'll give the definitions. What is the meaning of page fault? If required page is not available in the frame, if the required page is not available in the frame, page fault occurs. Now, can you tell me, logically, when the page fault occurs, MMU need to demand the page to MMU is a hardware. One thing I need to tell you, MMU is a hardware. is a memory manager, which is a software. Again, MMU is a hardware unit. is a software. MMU is a hardware. is a software. Now tell me, when the page fault occurs, when the page fault occurs? When the required page is not available in any one of the frame, then the page fault occurs. The required page is not available in the frame, page fault occurs. When the page fault occurs, what is the next step happens? Can you tell me, when the page fault occurs, what is the next step happens? Demand page happens. Page is demanded. Who will demand the page to whom? Who will demand the page to whom? MMU will demand the page to MM. MMU will demand the page to MM. When MMU is demanded the page to MM, what is the MM job? Whatever the page is demanded, it should load into some frames. Suppose this is first frame, second frame, third frame is not free, fourth frame is free. When I say it should be loaded into fourth frame, this page is loaded into this frame. Now that 150 becomes 450 because fourth frame. That logical address is 150, the physical address is 450. All of you are getting the point? What is this 50 here? As per our discussion, what is this 50? Offset. What is this 1 here? Page number. Now it got 4, frame number, 450. Now this will give it to them, that will execute. Again, what is the page fault? What is the page fault? If required page is not available in the frame, note it down, page fault, page fault. If required page is not available in the frame, if the required page is not available in the frame, then page fault occurs. Again, if required page is not available in the frame, then page fault occurs. If page fault occurs, what happens? Demand page happens. When the page is demanded, MMU will, when MMU is demanded the page to MM, when MMU is demanded the page to MM, now can I say MM need to load that page into the frame and update the page table? Once it is updated, can I say MMU in the place of page number, it will put the frame number and it will give it to the CPU. Now the CPU will fetch that. Now can you tell me, in this entire process, what we are trying to do? We are trying to save the RAM space unnecessarily. The entire process is not going to be loaded into the RAM. Again, in this entire scenario, what we are going to do is the RAM space is utilized properly. Entire process is not going to be loaded into the RAM for execution. A part of the process is going to be loaded. Is that point is clear? So who will maintain this page table? Who will maintain this page table? MMU will maintain the page table. So when MMU demanded the page, so MMU, when it is demanded the page, MMU demanded the page, job is to upload that page and update the page table. Once it is updated the page table, once it is updated the page table, once it is updated the page table, then it will get the what you call the frame number. Then it will convert that logical address into the physical address and give it to the CPU. Then the CPU will execute. Is that scenario is clear? The entire process aim is physically the RAM is not increased. The entire process conclusion is, will you agree, the physically the RAM is size is not increased? Yes or no? Physically the RAM size is not increased, but virtually it is increased. Please try to respond it. Physically the RAM size is not increased, but virtually it is increased. And entire process is not going to the RAM at a time. entire process is not going to the RAM at a time. A part of the process is going to, entire process is not going to the RAM at a time. A part of the process is going to, now tell me, virtual memory is divided into small portions. Those are called as, try to answer it. Virtual memory is divided into small portions. Those are called as pages. Physical memory is also divided into small portions. Those are called as physical memories frames. Page size and frame size both are, page size and frame size both are same. What the MMU will do, whatever the logical address MMU got, it divided into two parts. One is a page number and another one is a frame number. Sorry, page number and another one is page number and another one is a offset. Correct. After dividing that, what the MMU will do, it will check the page table. Is that page is already available or not? If not available, what happens? If not available, what happens? Page fault occurs. When the page fault occurs, demand page happens. Who will demand the page? MMU will demand the page to MM. Once the page is demanded to MM, what is the MM job? What is the memory manager job? What is the MM job? To load the page into frame. After loading the page into the frame, what it need to do? After loading the page into required frame, what it need to do? After loading the page into some frame, what it need to do? It need to update the page table. Correct. Once it is updated the page table, what the MMU need to do? MMU need to do the check the updated page table. It need to decide that page came into which frame. According to that, it need to calculate the physical address, give it to the CPU. Is that point is clear? This is how nowadays the things happens. So this is about the memory management and theoretical concepts. So no programmatical things are there. I hope in this module you got a little bit knowledge about Linux and system programming, IPCs, files and all those things. And Monday onwards, 2 o'clock, BE 8 and 9, 2 o'clock, TCP IP class will be there. Monday onwards, networking, 2 o'clock, pure online. And meeting ID password, within end of the day, they will share you through SMS. Monday onwards, TCP IP modules will be there, module will be there. Is it clear? Same 2 o'clock, it is a pure online. Siddiq sir is going, 8051 is an hybrid only. 8051, sir, where the page table is present? One of the student is asking, sir, where the page table is present? The page table, we can say in the in the place of memory management. Is it clear where the memory manager is present? In a kernel. Is it clear? So I'll try to upload this TCP IP meeting ID password in a Linux LMS. In a Linux LMS, I'll try to upload this TCP IP meeting ID password. And apart from that, you will get an SMS immediately after the class. Is it clear? Thank you very much for attending this session. I'm going to wind up.